third method of affecting a solution's formation rate is changing its temperature. At a molecular level, the increase in temperature causes the solvent molecules to move more quickly. This is due to the heat increasing the solvent's molecules' kinetic energy, causing the solvents to move more. Because of the increased movements, there are higher probabilities of the solvent and solute molecules colliding. These collisions break up the solute, increasing the speed of the formation of the solution. In the diagram, it shows the lower temperature solution having less movement, causing less collisions, while the higher temperature shows the opposite, with the formation forming more quickly. In a solution, separated solute molecules can return to the solute after being separated from the solute. This is known as recrystallization. In the diagram at the right, we see crystallization, with the solute separating and then returning to the solute. As the solute begins to dissolute more, chances of the solute's recrystallization increase, with more separated solutes being in the solution. Eventually, the rate at which the solutes separate matches the rate of crystallization. At this point, solution equilibrium is achieved, where dissolution and recrystallization occur at the same rate. With solutions, there are saturated and unsaturated solutions. In an unsaturated solution, the solvent is able to break down more solute and has not reached its limit. However, in a saturated solution, it has reached its maximum amount of solute dissolved and is unable to break down anymore. In the picture below, the left sponge would be like an unsaturated solution, still having remaining capacity. The right sponge would be like the saturated solution, both already reaching their maximum. However, there's a third form of a solution, supersaturated solutions. A supersaturated solution is formed beginning with a saturated solution and heating it up. By heating it up, its solubility increases and is able to dissolve more solute, becoming an unsaturated solution. Then, more solute is added to this heated solution until it becomes a saturated solution, now having more dissolved solute than before. By allowing it to cool slowly, it may become a supersaturated solution, where it is back at the original temperature but with more than the maximum amount of solute dissolved. The supersaturated solutions are naturally unstable. The picture on the right is an example of where a seed of a solute is added to the supersaturated solution, disturbing the unstable supersaturated solution and causing crystallization around the solute seed.
Solubility is the amount of a substance required to form a saturated solution with a particular solvent at a specified temperature. As seen in the example, 204 grams of sugar are required to form a completely saturated solution in 100 grams of water at 20 degrees Celsius. The temperature needs to be specified because changes in temperature affect solubility. For gases, increasing temperature increases the kinetic energy of gas molecules, making it harder to bond with solvent molecules and therefore making it harder to fully dissolve, decreasing solubility. For solids, increasing temperature generally increases solubility, but that is not always the case. As can be seen in the graph, the solubility of a potassium nitrate drastically increases with temperature, but the solubility of cesium sulfate actually decreases with temperature increase. Immiscible liquids are liquids that are insoluble in each other. For example, the polar water molecules in salad dressing attract each other and push out oil molecules, preventing the solution from remaining dissolved when left to sit. On the other hand, miscible liquids dissolve freely in each other in any ratio, like benzene and carbon tetrachloride. The reason why two nonpolar liquids like benzene and carbon tetrachloride are miscible is because the only intermolecular forces acting between the various molecules are London dispersion forces, which are quite weak. Because of this, the different molecules can bond to each other for dissolving. Polar liquids are also miscible with each other because the polar attraction between different molecules acts the same way as they would between a uniform liquid. While pressure has little to no effect on solubility for solids and liquids in a solvent, increasing pressure for gases increases their solubility. Gas molecules dissolve in a solvent by making surface contact with the liquid molecules. However, as a gas is dissolved, some of its molecules escape the solvent and go back to a gaseous state. An equilibrium is eventually established at which the rate of gas molecules switching between liquid and gaseous states is constant, solidifying the solubility of the gas. When pressure is increased, more gas molecules are pushed and forced to make contact with liquid solvent, becoming dissolved. More dissolved gas molecules offset the increased pressure but force more molecules to escape the solution. Eventually, the solubility equilibrium is reached at a higher solubility because the pressure forces more gas molecules to dissolve in a liquid. A statement from Henry's law describes that the solubility of a gas in a given liquid is directly proportional to the partial pressure of the gas on the surface of the liquid. If the pressure applied to a gas increases, then the solubility of the gas in a liquid it makes contact with also increases, and the same goes for decreasing pressure. A good example of Henry's law is soda. In a soda bottle, carbon dioxide is inserted at a pressure of 5 to 10 atmospheres, where its solubility is high. Once the cap is screwed off, the pressure drops to 1 atmosphere, and the solubility of carbon dioxide decreases. Because of the decrease in solubility, carbon dioxide attempts to escape the dissolved solution, forming gas bubbles in the soda.
Created using Powtoon.